So in today's tutorial, we are going to learn about something called pipeline hazards. Now, pipeline hazards occur in certain situations. You see, usually we expect in our computer system, a particular instruction should get executed in a single cycle per instruction. Now, what cycle per instruction is, we'll ask. For example, say in a given architecture, each instruction takes uh, 5 milliseconds to get completed. Then the length of the cycle is, duration of the cycle is 5. And if your program wants 10 such cycles, then total number of cycles that there will be required for the complete instruction or complete execution of the program is 10 cycles. So in our generalized sense, we need a particular instruction to get executed in a stipulated cycle. In other words, if you look into the diagram, in the columns we have the clock cycle number, right? And in the row, leftmost row, you have the instructions. Then, as we have discussed yesterday, in pipelining procedure, we usually try to divide our instruction into several sub-instructions so that each sub-instruction can get executed in a different segment of the CPU. Now, in this particular architecture, by looking at the table, you can say that you have 5 segments in your CPU. First one is instruction fetch, then instruction decode, execute, memory operation, then write back. Now, the idea is that in your CPU, you have set up 5 different segments in which a particular kind of sub instruction can get executed. Now, in ideal situation, our assumption, or at least we need that a sub instruction should get executed inside its stipulated clock cycle. What I mean to say, for example, in the first clock cycle, for the first instruction, which is load, you have invoked the instruction fetch sub instruction, right? So our demand is that it should get executed completely within the first clock cycle itself. Now, what if it cannot get executed in the stipulated duration of the clock? That means for each and every clock cycle, there will be a time duration due to some unavoidable circumstances. Say, instruction fetch operation here cannot get executed in the stipulated time duration available for the first clock cycle. Then what will happen? The thing will happen, or this phenomena is called pipeline hazards. So there are basically 3 types of hazards which occur in pipelining. First one is structure hazard. Now, in structure hazard, what happens? You see, hardware cannot support certain combinations of instruction. In other words, for a particular instance, say, 2 instructions in the pipeline require the same resource, right? Then structure hazard will happen. Data hazard, instruction depends on the result of the prior instruction, which is still inside the pipelining. If such a situation occurs, then we say that data hazard has happened. Then, thirdly, you have the control hazard. Now, it is caused by delay between the fetching of instruction and decisions about decisions which are taking place in the control flow. That means if else like things which we have discussed yesterday. Now let we discuss them one by one. So structure hazard, as we have mentioned before, arises because there is not enough duplication of resources, or in simple words, not enough resources, hardware resources are available in your architecture. Then structure hazard might occur. So here something is mentioned about how you can solve the structure hazard. Before that, let we look into the structure hazard phenomena itself. So this kind of table you can see on your screen, this kind of table is basically called reservation table, right? Let me write it for you. Reservation table. Now, you will ask the question, what is the purpose of this reservation table? Basically, inside the reservation table, you try to depict in which clock cycle, in which segment of the CPU, what instruction is being operated on. For example, if you look into the fourth clock cycle, you can say that first instruction, that is load type operation, is in the memory operation stage, whereas instruction 1 is in execution phase, instruction 2 is being operated in the instruction decode phase, instruction 3 is in the instruction fetch stage. So in this particular combination, structure hazard will occur. How? The question is how structure hazard will occur. For that, let we try to look into the problem in a more wider fashion. In a wider fashion, a machine, suppose a machine has shared a single memory pipeline for data and instruction. So I don't know whether this line is clear to you or not. Single memory pipeline, by single memory pipeline, this is an imaginary situation where we assume that in our computer architecture we have a single memory location available, right? That is the idea. That means not secondary memory, primary memory. If you look into the memory structure, here is your CPU, then here is your primary memory, then there is secondary memory. So the assumption is that at a particular time instance, the primary memory can hold information about a single instruction, right? So how structure hazard might occur in this case, the first instruction, which is a load type operation, that means memory operation will be involved here, as this is a load type instruction. Data memory reference will be here. So when the entire execution is in clock cycle 1, load instruction will be fetched in clock cycle 1. You can see it here. When in the clock cycle 2, load type instruction is pushed into the instruction decode segment of the CPU. So instruction fetch segment is now idle. So you bring or you fetch the instruction 1 into the instruction fetch segment. Now clock cycle 3, inside clock cycle 3, you can see that instruction load is in execution phase, right? And it is instruction 1 is obviously being decoded and instruction 2 is fetched. Then when the clock cycle begins, as it is a load type instruction, some kind of memory operation might be necessary here. Let we assume that memory type operation will be required here. In simple terms, you can think of it like CPU have to do some operation on the memory, right? In the fourth clock cycle. Here, right? Now, in the same clock cycle, if you try to fetch instruction 3, Once again, it means that CPU is trying to access the memory, right? But the memory for the time being is occupied by the load type instruction. So there is a hardware conflict. Two different instructions are trying to use the same hardware resource in the same clock cycle. So this kind of situation is called uh, structure hazard. Now the question is how you can try to solve this kind of situation, this structure hazard thing. So the idea is if you stall your CPU for a particular clock cycle, then you can see that the problem is resolved. Now, by stalling, don't take the word stall in generalized sense. By stalling from the perspective of pipelining, it means that you will not bring or you will not work on any new instruction on that particular clock cycle. For example, in the fourth clock cycle, if you look in the top diagram, you try to fetch the instruction 3, right? But here in the fourth clock cycle, you can see that the instruction 3 is not fetched, right? Rather, instruction flow, more precisely, if I say it, I can say it in that way that instruction flow is stalled for a particular clock cycle. No new instruction is brought into this particular fourth clock cycle. Now, what is the takeaway? What is the advantage we get out of this? We can see that now in the fourth clock cycle, the load instruction has done its memory operation peacefully. Now, in the fourth clock cycle, memory operation is done. In the fifth clock cycle, you can fetch the next instruction, which is instruction 3 inside the CPU, and pipelining goes on. So, in this is a way of solving structure hazard. Now, you can follow some other ways as well to solve the structure hazard. Some suggestions are solution 1, you can go for a wait as we have done in our example. Then what phenomenon you're going to face if you introduce this wait thing? So to introduce wait, you can see that first you have to detect that some kind of hazard has occurred or some type of hazard is going to occur. Only then beforehand you can know that you have to install you have to introduce a stall here. So then you need some kind of hardware resource or software resource to introduce this stall. That is the second requirement. And obviously this is going to be a low cost method, and it is the method is simple, but cycle per instruction is increased in this example. Now this is a practical scenario. This stalling thing, the stall thing basically is used in rare cases. Solution 2, you can use more hardware at the problem, right? So obviously if you can use more hardware, if you can recall our assumption, we have assumed that we have a single piece of memory location available here. Now if you have more than one piece of memory location beforehand, this kind of situation shouldn't have occurred, right? So if you you can use more hardware resources and pipeline those hardware resources as well. And lastly, you can replicate the resources. Now, from my opinion, using extra hardware and replicating resources are basically same thing, but being used from two different approaches. Because to replicate the resources, you need extra bit of hardware, right? For example, if you want to replicate this memory operation somewhere else and let the regular control flow happen, then you have to replicate this memory operation inside some extra piece of hardware, right? So these are basically some suggestions by following which you can solve this structure hazard thing. Then come to the data hazard. Now, data hazard occurs when there are data dependencies between different instructions. Generally speaking, there are two types of data dependencies: true data dependency and name dependencies. So, let we briefly look into these two kinds of dependencies beforehand. Now, an instruction J, follow carefully. You have two instructions I and J, right? Now, instruction J is data dependent on instruction I when either of the following holds. Instruction I produces a result that may be used by instruction J, right? So, how say instruction I looks something like A equals to B plus C and D equals to A minus 2. Now, surely you can see that instruction J needs some data which is being produced by instruction I, right? So, this is the first case of uh, true data dependency. And secondly, true data dependency can occur when instruction J is data dependent on instruction K, as it happened here. Instruction J is data dependent on instruction I, and instruction K is data dependent on instruction I. That means you have now a third instruction, say IJK, where you need E, you need to compute E equals to D plus plus. So you can say that instruction K is data dependent on instruction I. So if these two kinds of situations occur, then you can say that true data dependency is there in my instruction set, right? On the other hand, name data dependencies occur when two instructions use the same register or memory location called a name. Now, I believe that this is something, this name data dependency is something which you already know from other different subjects. Why? So, for example, say you have two instructions, one after another, like this: A equals to 2 plus 5, A equals to uh, B plus C. Yes, this is instruction 1 and this is instruction 2. Now, think about something. What happens when you declare a variable? When you declare a variable, particular variable, declare or define a variable, three things actually occur. Firstly, some free memory space inside your memory domain is reserved, right? The name which you have given to the variable is associated with that particular memory location, and the value is stored in that memory location. That means somehow with that memory location, you are associating the name of the variable. So if you have such situations, if you have data dependency in such situations, then you call it name dependencies, right? Now, name dependencies has also been clustered in two types. One is anti-dependency. Now, an anti-dependency between instruction I and instruction J occurs when instruction J writes a register or memory location that instruction I reads. Now, how it is like, how it actually looks like. So, think of our example in this way. A equals to A minus 1, right? Now you can see that instruction 2 is trying to execute something on some memory location which is being modified or written or being used by its previous instruction. Now, if you want that no kind of hazard should occur here, then you have to preserve this ordering. Now, why it is like so, you can think of it in either way. For example, before instruction 1, you have defined A as A equals to 1, right? Now, before executing instruction 1, let say we have executed instruction 2. Then what will happen if you execute instruction 2 before instruction 1? Then the value of A will be 0. 1 minus 1, 0. But according to our algorithm, the value of A should be 6, because in instruction 1, at the beginning, A is computed as A equals to 2 plus 5, which is 7. Then in the third instruction, that is instruction 2 in our example, A should be decremented by 1. So this kind of situation is called anti-dependency. On the other hand, you have an output dependency when instruction I and instruction J write the same register or memory location. Then once again, ordering between the instructions must be preserved. Once again, in this example, we have both anti-dependency and output dependency because the output from instruction 1 is being used in instruction 2. In that sense also, you have to preserve the ordering of the instructions for successful execution of the algorithm. Now, by following this kind of dependencies, you can classify the data hazard. Now, once again, data hazard is something where uh, there are data dependencies between instructions. Now, let me try to figure out what different types of data hazards might occur in our system. Now, data hazards can be classified into three categories: read after write hazard, then write after write hazard, and write after read hazard. Let we look into one by one. First, read after write hazard. Now, look into these two instructions. R1 equals to R2 plus R3. That means in instruction I, in the first instruction, the CPU is told to add the values inside register R2 and R3 and add the result, sorry, add the values inside register R2 and R3 and store the result inside register R1. Then in the next instruction, you are told to subtract the values inside register R1 and R3 and store the result in register R4. Then what will happen? How data hazard will occur here? Read after write hazard will occur here. Let's try to figure out. Uh, Now, instruction 1, let we write it, add, and let we write the clock cycles 1, 2, 3, 4, 5, 6. And instruction 2 is the subtraction instruction. First, instruction 1 will be fetched in the clock cycle. In the second clock cycle, it will be decoded, and second instruction will be fetched. Now in the third instruction, it will be executed. No, sorry, fetch operand. The operands necessary for instruction 1 will be fetched from memory instruction decode, then execute and fetch operand for instruction 2. Now, at this point, read after write hazard will occur. Why? Now, here, when this is instruction 1 is being executed, everything is inside the CPU for the time being, right? Now you can see that the result of addition in between R2 and R3 is not available inside the memory. It is inside the CPU, right? But during the same clock cycle, you can see that fetch operand sub instruction is invoked for instruction 2. That means if instruction 2 tries to fetch the value of R1, then it is obviously going to get some kind of garbage value here, right? This kind of hazard is called read after write hazard. Now, in the next stage, what will happen? You see, instruction 1 will go through the write back procedure. Once the write back is complete, then only the correct values for operands inside the subtraction instruction can be fetched from the memory. So what you have to do, you have to introduce no operations. You cannot do any operation for instruction 2 here if you want to solve this situation, right? Once again, to solve this problem so that your operands for subtraction instruction, which are R1 and R3, be made available inside the memory, the write back operation for instruction 1 must be completed. So to solve this, you did no operation on instruction 2 for 2 subsequent clock cycles. And in the clock cycle 6, you have invoked the fetch operand for instruction 2. So that is the idea of write after read hazard. Read after write hazard, sorry. That means you can read the operands for the next instruction, only the previous instruction has written the memory, right? Then come to the write after write hazard. Now look into the instructions carefully. First one is subtract R4, subtract R3 from R4 and store the result in R1. And instruction J is add the values of R2 and R3 and store the result inside R1. Now, write after write hazard. Write after write. Let the first instruction be written inside in the memory first, then only do the write operation for this instruction. Why it is like this? Just once again, follow this. What if what if instruction 2 writes the result before instruction 1, right? You will never have the output from instruction 1, right? Because it will be overwritten. So this kind of situation is called write after write hazard. Now, what is the solution? The solution is register renaming. How? Now, if you rename this register R1 to something else, now we don't have the problem which is arised out of same memory location referencing, right? So rather than R1, if we use uh, R5, R6, then two different memory locations are basically referenced in two different instructions. So in this situation, write after write hazard will not occur. Then last one is write after read. Now to understand write after read, let we look into these two instructions. First one is subtract R3 from R1 and store the result inside R4. Then inside the next instruction, that is instruction J, you are adding the values of R2 and R3 and storing the result inside R1. Hope you have got it. Now you can see that there is some correlation between these two instructions. How? The operand here is R1, which you should read from the memory, right? And in the next instruction, you are storing the result into the same location, which is an operand for the previous instruction. So, first, in the first instruction, R1 is supplying some value which is necessary for computation. It is providing input, and in the next instruction, R1 is storing the output, right? Now, if you follow the sequence of instructions, as we have discussed sometimes before, let's say R1 has some value called 1 before instruction I, right? Now, if you allow instruction J to write back, right? Before the reading operation, fetch operand operation for instruction I gets completed, what will happen? Just as we have discussed in our previous example, if you let instruction 2 to get executed before get written back before the fetch operand for instruction 1 is complete, or then you are going to get an old value or some faulty value for the first instruction itself. It is going to get the updated value here from add operation, but it should not use it. It should use some previous value for R1. So this kind of situation is called write after read hazard. That means you should write once the read operation from the previous operation is complete. So in a nutshell, let we try to look into the look what should ideally happen in this three different kinds of situations. First one was read after write. That means once the previous instruction has completed its memory writing operation, then only the next instruction should read the values from the memory. Write after write, once the previous instruction has completed its writing operation, then only the next instruction should write. And lastly, write after read. Once the previous instruction has read the value from memory location, then only the write operation should commence from the next instruction. So this was data hazard. So you can follow this diagram to understand and play with this data hazard thing yourselves and try to introduce this NOP, no operation things, NOP, no operation things, whenever necessary. Just play with it. Now, let we come to control hazard. Control hazard occurs when we need to find the destination of a branch and can't fetch any new instruction until we know that destination. So I believe somehow we discussed this yesterday. Just once again, if A greater than B, statement 1 should get executed, else statement 2 should get executed. Now, suppose you have fetched this if instruction inside the CPU for execution. So, in the next stage, it gets in the decode segment. This if instruction goes to decode segment in the next clock cycle. That is fine. Now, you cannot fetch any new instruction inside the CPU. Why? Because until this logical operation A greater than B gets evaluated, you don't exactly know among S1 on or S2 which instruction to be fetched, right? Then what is the solution? The solution is to stall bringing of new instruction inside the CPU for some clock cycles until this branch instruction, this condition gets evaluated. So the solution is pretty straightforward. So these were different kinds of hazards and some of their possible solutions which you can apply to solve those hazards. So let we end our tutorial regarding hazards.